previously we did an example of dynamic programming on a tree. Then we placed that in a slightly more abstract setting and gave a definition of a dynamic program and wrote down the expression and proved why Bellman's equation holds there. Okay, and now we're going to use it for something that's a bit closer to a financial type of application. All right, so let's consider the following setting where we've got an investor who has a fund. Okay, and in that fund there are X pounds. Okay, at time 0. And it's a specific type of fund where the money that is put in the fund can't be withdrawn, but it pays interest. Okay, it pays R% interest, and it does that for T years. Okay, and at each time the investor can make a decision. Okay, it can decide to consume the wealth of the interest, or it can decide to reinvest it into the amount X. All right. So let's say that the investor decides to consume a proportion A of T of the interest, okay, and the remaining is reinvested into this pot of money in the investment fund. Okay. So we're going to answer the question of what the investor should do to maximize their consumption. Okay. So to maximize the amount consumed from the interest of the fund. Okay. Right, so let's answer that. Okay, so first things first, let's draw down the plant equation for this problem. Okay. Okay, so what we want to do is get an idea of how we get from the amount of money that we have at time t in the fund to the amount of money that we have at time t+1 in the fund. Okay. Well, we know that this pays an interest of R. Okay, so that's the interest that we get. And then we know that AT of that we consume, and so 1 minus AT of that is then reinvested back into the fund. So the amount of money that we have at time t+1 is equal to the amount of money at time t plus the amount of money that's put into the fund at time t from the interest. Okay? And then our objective, the thing that we want to maximize, that is to maximize the sum of the amount that we consume. So from time t equals, let's say it says from time 0, time t equals 0 to time t minus 1, r of x of t times a of t. This is the interest I get from the fund at each time. That's the amount that I consume from the fund each time. Okay. Okay, so now we're going to apply exactly the same ideas that we've been working with this tree example and with the definition of dynamic programming, that we're going to try and solve the problem by starting at the end of time, okay, so at the leaves of the tree, and then working our way back to time 0, to the root. Okay. It's exactly the same principle, but applied in a slightly different setting. Okay, so let's say that. Let's apply the same idea as before and solve backwards in time. Okay, so let's start at time little t equals capital T minus 1. So the last time that we've got the choice to consume some of the wealth that's in the fund. So the last time that we have the choice to consume some of the wealth in the fund. So the last time we get the chance to consume some of the wealth in the fund. Okay, let's think about it. We've got an amount of money, xt minus 1. We can't withdraw any money from the fund. Okay, we're going to get some interest r of xt minus 1. And then after that, I can't get any money out. So I might as well take the most that I possibly can. All right, so here, it must be that a of t minus 1 is equal to 1. All right, and so w of t minus 1 of x of t minus 1 is equal to r of x of t minus 1, since you're consuming everything, all of the interest. Okay, so your reward, optimal reward for the last time period, is all of the interest that's available. Okay, so you don't want to save anything for a later date. Okay, all right, so now think of that as us solving one stage back from the leaves of the node, from the leaves of the tree, sorry. We've done the first time period, now let's go to the next. So at time t equals t minus 2, okay, let's look at what's going to happen in that case. So we can kind of resort to our good friend, the Bellman equation. So let's because from that we can use the solution that we had at time t minus 1 and introduce it, push it back to our solution at time t minus 2. Okay, so if we're looking for the optimal reward at time t minus 2, okay, it's going to be to maximize the consumption at time t minus 2 plus the reward that I receive. Okay, so that's all the interest that I get to consume, plus, well, I'm going to end up in a new state at time t minus 1, x of t minus 1. Okay, and then I know from up here that this is equal to r of x of t minus 1. Okay, so I can then substitute this into the next line. Okay, so what I'm going to have here is the maximization of the same expression as before, r of x of t minus 2, a of t minus 2, plus r times x of t minus 1. Okay, I can write that in a slightly different way. Note that I know that x of t minus 1 satisfies the plant equation over here. All right, so I know that this is x of t minus 2. Notice here I'm just using the same expressions up here, but with this as x of t minus 1, and this is x of t minus 2. Okay, plus r of x of t minus 2, 1 minus a of t minus 2. Okay, so here that's the amount of money I had at time t minus 2, and that's the amount that I reinvested because I didn't consume, that went into the value of the fund at time t minus 1. Okay, so in other words, this is x of t minus 1. All right, so now I can just start to tidy up this expression a little bit. So here Notice that there's an r of x of t minus 2 in all of these expressions, so I can take that out. Okay, and I can also tidy up the terms a bit here. Some of them have things to do with the action that I'm taking, the amount that I consume, and some of them don't. Right, so I'll just collect terms together as appropriate. Okay, so I can notice that there's a 1 plus r plus 1 minus r a of t minus 2. All right, and I can just, let me just move that over a little bit. I'm going to maximize that guy over the actions that I can take at time t minus 2. All right, so notice this is actually a really easy optimization problem to solve. Okay, so in particular, notice that this is just a line. Okay, it starts at height 1 plus r, and then depending, and has a slope 1 minus r. So depending on the slope of that line, if it's a positive slope, which we'd usually expect, okay, then we've got a line going up here, and if I look at the range of a from 0 to 1, if it's a positive slope, then we're going to end up maximizing at 1, okay, over here. But on the other hand, if the slope was actually negative, right, we're going to maximize over here at a equals 0, all right? So in other words, it's going to be the maximum between the two endpoints, all right, in either case. So it's either going to be that a is equal to 0, okay, so you invest nothing, and in this case you get 1 plus r, okay, sorry, you consume nothing, or you consume everything and we get 2, and we're going to take the bigger of those two options, okay? All right, so we've got one option that corresponds to consume everything and one option that corresponds to saving everything, okay? Right. So we can think of this as the 1 plus r being I invest and get interest of the total compounding of the wealth is 1 plus r if I save interest and then I take that out, or I get 2 payments, okay, that are equal in value from the interest to the fund, okay? So that's the 2 consumptions, or that's the non-consumption and then consumption with 1 plus r interest, okay? So, okay, so at this point, we could then go to this time t, capital T minus 3, capital T minus 4. And what happens is we begin to spot a structure here that we can already begin to see already. Notice that the solution is always r times x times something, all right? It doesn't have to necessarily do with x. Okay, so we can kind of guess the form of the solution of this, and we can then use kind of induction, going back from capital time t to 0, to guess the form of the solution, all right? So let's do that. So now, at time little t, capital T minus s, okay, so at time t equals capital T minus s, let's suppose that the next reward function, okay, has the following form. It's x of capital T plus 1, and it's again, the reward times the consumption times rho capital T minus s plus 1, so some factor that I've multiplied on. So in this case over here, this is rho of t minus 2. Okay, we want to know how this is combined together to give the next value, right? Okay, if indeed it does combine together to give the next value. Right, So we can follow the same steps as before. Okay. Notice that Wt minus S is equal to, well, I could arrive at a similar Bellman equation expression. I'd substitute in the form of the next reward function, this, okay. Then I could apply the plant equation and then rearrange to get a new expression, right? I'm not going to do all the calculations, but I'll imagine I've done the substitution here. I'll imagine I'll have applied the plant equation here, and then you can check for yourself at home that we're going to arrive at an expression with the following form. So we're going to get r times x of t minus s, and then we've got a choice to maximize, okay, over the actions between 0 and 1 of, now the form is going to be 1 plus r times rho of t minus s plus 1 plus 1 minus r rho of t minus 1 t minus s plus 1, okay, times a of t minus s. Okay, so that's going to be what we're going to get by doing exactly the same steps previously. Okay, once again, it's a line. Okay, so depending on whether this term is positive or negative, we're going to decide either to consume or not consume. Or let's say we're going to decide either to not consume or consume. If it's negative, okay, it's better to do a equals 0. And if it's positive, it's better to do a equals 1 and consume everything. Okay? So, we're going to have that this is equal to r of t minus s, and then depending on the outcome of these two, I'm either going to have a solution where a equals 0, which is going to give me rho of t minus s plus 1 times 1 minus r, sorry, 1 plus r, okay, or a equals 1, okay, in which case I'm going to get that this term is going to cancel with this term, and I'm going to get rho t minus s plus 1. Okay, right. Now I could define this guy to be my new value of rho of t minus s. Okay, so what we arrive at is an expression rho of t minus s is equal to rho t minus s plus 1, 1 plus rho max. Okay, so remember this expression means the maximum between this term and this. 1 plus rho of t minus s plus 1. Okay. Okay. Now it doesn't seem like we've got very far. We've gone from one recursion to another recursion where we've got rid of the maximization in it at least, or most of the maximization. Okay, but we're actually in a situation where there's something we can kind of interpret as answer. Okay, so first thing to note is that this 1 plus r term corresponds to saving till the next round and then compounding the interest. Okay, so this term here means save and consume nothing. And this term here means consume everything. Does So the 1 here meaning consume everything, and then we've got the proportions, some of the proportions of consumption from there on out. Okay? All right. So now let's draw a picture of what's happening. I'm not very good at drawing, so apologies. So here, let's have row, and then notice we can draw the 2 lines corresponding to these as a function of row. Okay, so we've got a line that's 1 plus row, and then we've got a line that starts at 0 and then goes up at slope 1 plus r. Okay, so this is the line y equals 1 plus row, if this is the y-axis, and this is the line, I'll keep it going, y equals row 1 plus r. Okay, and notice eventually they're going to swap over. So on this side here, okay, this area up to here, okay, 1 plus row is bigger, okay, so that means consume everything. Whereas on this side, from here on out, this line that corresponds to saving is optimal. So save everything. Okay? And this line keeps on going forever. Okay? Now, we know at time 1, with 1 unit of time to go, so at time t minus 1, we know this is equal to 1. It's optimal to consume everything. So we can look at this expression and see what the recursion is going to give you. Well, we're going to find that the maximum is given here at 1 plus row. So the value here, although it's badly drawn, is 2. Okay, and that gives me the next value. Okay, so then I can plot that. Row of t minus 2 is equal to 2. Okay, and I can look up here and I get the next value. Okay, once again we see this line is above, so it means to consume everything, and I can keep on going. Okay, but notice eventually I'm going to pass over this intersection point. I'm going to keep adding 1 to the value each time until eventually we hit a point row of S star. Okay, and at that point, the first time we pass over, the maximization is going to be here. All right, so the optimization is going to switch from a policy that's consume everything to a policy that at least at this time says save everything. And the new point I'm going to get here, a row of S star plus 1 is equal to 1 plus r of row of S star. Okay, so that's going to be a little bit further out over here. Okay, and then it's just going to keep on expanding outwards. Okay, so what does that mean? So it means at the last time, for the last S minus 1, S star minus 1 years, it's optimal here to consume everything. But before that, it's optimal to save everything. Okay, so you can think of this a bit like an annuity or a pension scheme, where what one does is during your life, you save and you save and you save up a lot of money. It compounds with interest over time, and then as you reach towards the end of the time period that you live for, you decide to then take out and consume your savings that you've compounded over time. So the optimal strategy is at some point, maybe 60, 65 years old, you decide to move from a strategy that's saving to one that's consuming, and then from there on out you save until the end of time, capital T. Okay, so it's strikingly similar to a lot of the ways that people do savings, say around pensions. Another thing to say is this type of control, which although we're maximizing over a continuous range of values, okay, so the actions that we made were not like in the tree example where it's left or right, but continuous. But because the problem was linear, we found that the solution was either to consume everything or to not consume anything. Okay, so it's sort of all or nothing. These sorts of control policies are sometimes called bang-bang control policies and are very common and popular. Okay, right. Okay, so next we'll start to try and introduce some notions of probability into this. Okay.